This is lecture 9D on the solution of the RL and RC circuit equations with a sinusoidal voltage input. I want to do another solution, and in this case the voltage is not constant. Before we did it, the voltage was constant, like using a battery. Now we're going to say the voltage is a sinusoidal voltage, has some peak times sine omega t, as though you connected the circuit up to your household current, for example. Let's see what kind of solution we get here. So now we had before, I'm going to write it just for the RL circuit, I of t equal e to the minus r over L times t, 1 over L times this integral of e to the r over L times t times the voltage So here's the voltage, and because the voltage is now sinusoidal, I have substituted the sinusoidal voltage into here. And now I'm going to try to solve for it. Okay, what have I got? I have the peak voltage can come out, because that's just a constant, and I'm left with the integral of an exponent times the sine wave. The integral of e to the at times the sine of bt is given in table of integrals in the back of Stewart, or you can find it in another reference book. Because we're just trying to show the solution and not work out this integration problem in detail, I'm going to go ahead and grab that solution and use it. And here is the solution right here. That's an alpha, by the way. So the integral of e to the at sine bt dt is e to the at over a squared plus b squared times a times the sine of bt minus b times the sine of bt plus alpha, which is some constant. That's kind of looks like the a's, but this is an alpha. It's just a constant of integration. And I'm going to use that result. In our case, this a here is r over L. And the b is omega. So I can just substitute that in. So this is the integral I want, e to the r over lt times the sine of omega t, and I get e to the r over lt, and I get this denominator. You can see where those terms come from. Well, just a minute, okay, here's your b, the b is omega, here's your omega squared. Fine. Here's your a is r over L, here's r over L squared in the denominator. Okay, that's fine. And now a times the sine of omega t plus b. Whoa, I went ahead and put 120 pi like it was 60 cycle. That should have just been omega. Let me fix that. That's just omega. Should have just been omega here. I put in a specific frequency and you don't need to. Okay. Plus that constant of integration. And now I'm going to, if you remember before, the solution, there was a term, e to the minus r over lt, multiplying everything, and I'm going to distribute that through. When I distribute that through, this goes away, and I just get v over L times 1 over r over L squared plus omega squared times r over L times the sine of omega t minus omega times the cosine of omega t, plus the constant of integration times this decaying exponential. So what do I have here? I have a transient solution here. This actually is a steady state solution. It does depend on time, but it does not decay away. The transient solution decays away, and you're left with the steady state solution. In many circuit classes, these transients are ignored because they can happen very, very fast, so fast that maybe you didn't even measure that. And they're only concerned with what's left over, called the steady state solution. In the first example where I identified the steady state solution, it did not even depend on time. Here it depends on time, but not in a decaying way, instead in an oscillatory way. So here's a graph of a solution for some particular values. Let's say we have a 60 milliohm resistor, the inductance is 1 millihenry, and using household current. Okay, the 60 cycle, not the dryer circuit, just regular household current. Right. Here's what the current's going to look like. Initially, just look right in this region here. there was a transient, e to the minus r over lt. That decayed away, but while it was active, it influenced that sine wave. But you see, the sine wave looked like it was a little bit off of, and then it settled off of the average value of 0. It was, in fact, didn't even just look like it, it was off of it, and then after a while, it settles down. So the transient is marked here. The transient was this term right here, and it's decaying away. Like I say, usually those aren't even talked about in some circuit classes, in some, some cases, because it will decay away very fast, and then you're left with this other, which is this part, the steady state value. And now I'm going to look at a comparison between these solutions and the graphical